in the last few lectures, we derived the posterior for our problem of tossing heads and estimating the parameter of the coin. And we chose beta as the prior, and binomial was the likelihood function, so which combined in conjugacy to give us a beta posterior. So the posterior on distribution is distributed as a beta distribution with parameters beta h plus alpha h, beta t plus alpha t, where beta h and beta t are coming from the prior, alpha h and alpha t are from beta, number of heads and number of tails respectively. Now theta is what you want to estimate. Theta is the probability of the coin landing heads. Now, to use Bayesian inference, we are going to use probability of theta given d. We are going to use the posterior distribution, this right here. We're going to use this distribution to estimate theta. And since it's a distribution, to sample from it the best sample that corresponds to our theta value from this distribution would be equal to the expectation of theta under this distribution. So a generic form would be expectation of f of theta, where f of theta is any function of theta. We could be interested in theta or some function of theta which could be our parameter. So it's just a generic form here in which we are going to explain this, but if theta is our parameter of interest, this just becomes expectation of theta instead of expectation of f of theta, but it would be similar. It would look similar. F of theta would just be equal to theta. And how to calculate the expectation of something under a distribution. So now theta we know is distributed according to the posterior, p of theta given d. So now to calculate the expectation, we integrate 0 to 1 f of theta, p of theta given d, d theta. This is just follows from the definition of expectation. And now we have an integral here and not a summation. That's because p of theta given d is distributed as a beta distribution, which is a continuous distribution. And since it is continuous, we should have an integral here instead of a summation. If it is a discrete valued distribution, we will have a summation here. And this is how we do the expectation. So now, to estimate theta, we have to solve this integral. And that becomes problematic in many cases. The integral is often very hard to compute. And in those cases, we still want to go ahead and be able to estimate theta. And that's when map estimation comes to play. Map estimation or maximum a posteriori estimation is another way to estimate theta. So we already looked at MLE, maximum likelihood estimation. So this is another way to do it, which uses the posterior. Just to remind you, maximum likelihood estimation, MLE, uses the likelihood function for estimation, and map uses the posterior. So now posterior we know is a combination of likelihood and the prior. So it already includes the likelihood but also has some additional information in the form of the prior. So to solve map, we want to use the similar technique that we used in MLE. We want to find the most likely parameter to approximate the expectation. We want to do an argmax over theta in P of theta given D. So find the value of theta that maximizes P of theta given D. Now, if you remember what we did in maximum likelihood, we had a very, very similar form. This was entirely similar, except that this part was replaced with the likelihood function. All right, now we have this form and with the posterior, and we use that to estimate theta cap, or we can also call it theta map. And instead of computing the expectation, which also involves computing the integral, what we do is that we approximate the expectation to be equal to the value of the function at theta map, at the value that you have just estimated by computing an argmax of theta over P of theta given D. So now this is again generic. We assume any function of theta as our parameter, but if theta is our parameter, then we would just return theta map as our estimated value. Now, let's look at how to compute map for beta distribution. So first off, we need to expand P of theta given D. We know that it is from a beta distribution, and we know the parameters are beta H plus alpha H, beta T plus alpha T. These are the parameters. And now we expand beta according to the formula for beta, and we get this entire equation here when we substitute the parameter values. So from here to computing theta map, what is the next step? So we want to find the argmax of theta. What is the value of theta that maximizes this entire equation here? And we have solved this before for MLE. We use a similar technique here. We differentiate, set it equal to 0, and solve for theta. So we differentiate this with respect to theta because that is what we are trying to maximize, and we set it equal to 0 and solve for theta. And if you do that, you will get this value. And this I will leave as homework, and I would like you to solve this and get back to me if you are not able to. Differentiating with respect to theta and setting it equal to 0. Another trick to keep in mind when doing this is we have a multiplication here, and similar to the MLE formulation, we could use a log, which would simplify our differentiation and setting it equal to 0 without affecting our result. So that's what you should do. Similar to MLE, take a log and then differentiate, set it equal to 0 and solve for theta. So we can see that in essence, the beta prior is nothing but some extra number of coin or thumbtack flips, right? So because that's what the parameter value just adds to the number of heads and number of tails here, right? So beta prior is equivalent to an extra number of thumbtack flips. If we have infinite data, if we have lots and lots of data, infinite, then the prior is forgotten. We saw this in the example, the 3 examples that we discussed for different priors and different data set values. And we could see that as the data set size increased, the prior mattered less and less. And if the data set size is infinite, of course, the prior is completely forgotten because it's not significant when compared to infinite data. But we also saw that for small sample size, for example, when we had 4 total number of flips recorded and 2 heads and 2 tails, then we saw that the prior is actually really important because it can have a good amount of effect on the posterior and hence your final theta value. So keep that in mind that as n tends to infinity, phi is mostly not does not matter much, and it could just not be relevant in the posterior, and it's in that case a map would sort of approach MLE because the data is what is driving it, and MLE is based on the likelihood, which is based on data, and map is based on prior, which is now forgotten because we have infinite data. So this is also going to be affected more by the likelihood, and then they approach each other, they look similar because the prior is now forgotten.